Hey guys, welcome to the video tutorial over Snell's law. So this video tutorial is going to cover the basics of Snell's law, of course, and then reflection and refraction a little bit, and then some other useful equations and some demo that will greatly help you. So Snell's law says that n1 sine of theta 1 plus, or equals rather, into sine of theta 2. Now this n is the index of refraction, and it increases or decreases depending on the material that your light is going through. Air, we will say that its index refraction is 1. Now, technically it's not, but let's not get into that. Another useful equation is the equation for the critical angle, which sine of our critical angle is 1 over n. Now that critical angle is the angle needed in order for the light to completely reflect in the medium and stay in that medium. And you know that comes up sometimes on a multiple choice. What type of angle would be needed in this type of medium? It's just a simple, just know this equation. Really know this equation. But if you want to get a couple points, you should know that one. Now some other useful equations when dealing with Snell's law is F equals our velocity, or sometimes how we've written it, F equals C over V, or excuse me, C over our wavelength. Again, we know that the frequency doesn't change, and so if we know the wavelength or if we know the speed of light, blah, blah, blah. One other useful equation is N1 over N2 equals V2 over V1. So that's something, again, useful depending on what type of problem you have. Now, the main thing to remember is whether the light is going to slow down or whether it's going to speed up. And that all depends on the two mediums that you're going through. So let's say that we are going from air to water. And water usually has an index of refraction of 1.3. And so here we've got a ray coming in, and it reflects off of the normal, okay? And so the normal is what is perpendicular to my surface. So my normal comes straight up like this, okay? And it also comes straight down like this. Now, again, part of the ray will reflect off how we know law of reflection that says that our angle of incidence is going to equal our angle of refraction. So in other words, this angle, oh, I'm still on the line tool, silly. In other words, this angle will equal this angle. Now that's a law of reflection. Now refraction, since this light is going to slow down, then it is going to bend toward the normal. Okay? That's one of the most useful things when dealing with these types of problems. So it slows down because I'm going from a low index of refraction to a higher index of refraction. And so let's say I'm leaving now the water and I'm coming out back into air. Well, you would draw your normal again. So coming straight up, coming straight off. And then you would know that your light is going to bend away from the normal because it is speeding back up. And so you could do something like that. And these first two lines will be parallel. So if you were given a problem like that, you would know, oh, this medium and this medium must have the same index of refraction. So just know that if it slows down, it bends towards the normal. If it speeds up, it bends away from the normal. And we can visualize that using PhET, which should have been pulled up, but, oh, there it is right there. Okay, so here we're going from air, and we're going, I don't want to go to a mystery material. I just want to go to water, or glass. Let's go to glass, whose index of refraction is 1.5. So you see how there's my angle, and you see how it bends towards the normal. Now, it doesn't bend very much, but it does bend some. If I have water, which has a lower index of refraction, it bends even less. But if I increase that index of refraction, it gets closer and closer towards the normal. And if I lower my index of refraction, it keeps bending away from the normal until I have air again, and then it just stays straight. So this works the same if I'm going from water to air. Here it speeds up, and so it bends away from the normal. Okay, those are probably the most useful tools that you can use to attack those types of Snell's law problems. The ones that aren't just a simple, here's the index, here's the angle, plug it in. Know that if it speeds up, it bends away. If it slows down, it bends toward.